I'd like to thank the organizers for the invitation. So I'll skip over this introductory material. Just briefly, the BKL conjecture has 3 points. A generic spacelike singularity is basically the dynamics is vacuum dominated. Matter doesn't matter. It's local or silent. Spatial derivatives are negligible. And the dynamics is oscillatory, bouncing between Kasner states. To set up for spike dynamics, I would review spatially homogeneous or Bianchi spacetimes. The main building blocks of what we know before spikes were discovered, the main building blocks of the BKL dynamics are made of the Kasner solutions and the Taub solutions. So Kasner solutions appear as fixed points or equilibrium points, saddle states, and Taub solutions appear as orbits connecting these fixed points. So Taub solution describes transitions between Kasner states. And these are Bianchi type 1 and type 2 solutions. Okay, and I'm going to talk about the dynamics. So I'll be using a lot of dynamical systems jargons here. I mean, state space, equilibrium points, orbits, attractor, and so on. Some mathematical setup. The orthonormal frame formalism. The basic variables that we use. We have a tetrad, and we decompose the covariant derivative of the time-like congruence 4-vector U into these irreducible parts. So sigma are the rate of shear tensor, omega vorticity, theta is the rate of expansion scalar, and u dot the acceleration vector. But was set the vorticity to 0, so omega doesn't appear. Okay, and the Hubble scalar h is used in place of theta, so h is equal to 1/3 theta. Now the tetrad or the orthonormal frame vector fields are related to the coordinates t and x I as follows. So E alpha tetrad, the 3 spatial ones are related like this. So E alpha I are the coefficients, the frame coefficients, and N is the lapse. The main point is that these vectors do not commute. And the coefficients are as follows. Again, the E0 with E alpha commutator, the coefficients, you get the U dot and H and sigma, and an extra capital omega, which is the frame rotation rate. And the spatial commutator gives you A alpha and N alpha beta. And this A and N alpha beta determine the curvature of the spacelike slice, T equal constant slices. So basically they are building blocks of the spatial curvature. Okay. Hubble-normalised variables. So variables are made dimensionless by dividing by h. Okay, so for example, a and n here, after dividing by h, I use capital A and capital N, also with superscript h, to emphasize that they are Hubble-normalised variables. And they are nice because they reflect that self-similar solutions are represented by fixed points in the state space. Okay. Spatially homogeneous solutions or Bianchi solutions. They're classified by looking at whether A alpha is 0 or not. So that's class A and that's class B. And the Bianchi types are classified by looking at the eigenvalues of n alpha beta. So Bianchi 1, the n alpha beta is 0. Bianchi 2, n alpha beta has 1 non-zero eigenvalue. And it can go on to the most general case, Bianchi 9 or Bianchi 8, 3 non-zero eigenvalues. The Kasner solution represented in these Hubble-normalised variables simply described by a circle of fixed points. The two variables involved here are sigma plus and sigma minus. So, and the sum of squares is equal to 1. Whereas the Taub solution is described by an orbit. So it has one extra variable because this n has a non-zero component, let's say n11, and it satisfies this constraint. It's an orbit connecting two Kasner points, as we'll see. So these are three orientations of the Taub or Bianchi II orbits projected in the sigma plus, sigma minus plane. So this picture corresponds to n11 non-zero, and this corresponds to n22 non-zero, and this corresponds to n33 non-zero. I draw this triangle to help you visualize how these orbits, they look like they are emanating from this corner of this triangle. Okay, it's very easy to draw these orbits. Now, in the three-dimensional state space where if you draw n11 out of this page, then this orbit are actually on an ellipsoid because of that constraint, of this constraint, right? So this orbit actually, if you also draw the n11 direction, it lies on, an orbit would lie on an ellipsoid. And n11 can be either positive or negative. So it can go above with n11 positive or go below with n11 negative. Now, these orbits are building blocks. So if you consider Bianchi 8 or 9, all three n components or n eigenvalues are active. So for example, if you start here, the Bianchi 2 transition will take you there, and then the next Bianchi 2 transition will take you there, and so on. So you bounce around the Kasner fixed points or Kasner circle indefinitely, and this is the BKL or mixed master transitions dynamics. You see, for example, over here, there are a pair of blue and green bounces. So let me introduce another terminology here, Kasner era. So when a pair of n's eigenvalues are active, you have one Kasner era. Eventually, you come to a point where another pair, the red and green eigenvalues are active. Then you start to call that next Kasner era. And each fixed point here represents one Kasner epoch. So a Kasner era is a string of Kasner epochs where a pair of n eigenvalues are active. And then when you switch pair, you enter another Kasner era. BKL introduced a very convenient index, BKL index U, to describe each Bianchi 2 transition. So for each Bianchi type 2 transition, this index u reduces by 1 if it's bigger than 2, and if it's smaller than, you take the inverse, 1 over 1 minus u, u minus 1. Okay, so it's a very simple description here. And this foreshadows what's to come for spice. For spice, it's going to be u minus 2 rather than u minus 1. For vacuum Bianchi VI and VII, these models can sustain only one single Kasner era because it has only two non-zero n eigenvalues, and they don't rotate. Well, they rotate on one axis. Okay. So this is actually the Taub or Bianchi II orbits. So with the n minus basically stands for maybe n22. And this is the frame transition, which is which the u index doesn't change during this transition. Okay. So with these two sets of transitions, you get this following zigzagging, bouncing between the Kasner states, but eventually you end up at this arc here where you can't do any more transitions. So you get one Kasner era and that's it. And then for Bianchi VI, this is the exception of Bianchi VI minus the ninth. You have the following sets of orbits. And these two are frame transition sets. With this extra third set, this one is able to sustain the BKL dynamics indefinitely. So you get more than one Kasner era. Okay, now, no, it's just a notation to mean exceptional. Is a notation in the classification. Okay, let's move on to the so-called OTG2 spacetimes. These are vacuum models with two Killing vector fields which act orthogonally transitively, hence the OT. Okay, so a special class of G2 models. And it contains the Bianchi VI 0 as a spatial homogeneous limit. And what's new here, because of inhomogeneity, the eigenvalues of the n's can have 0. So the eigenvalues of the n can change sign in your initial data. So it could be positive here and negative there. If the eigenvalue of n is 0, it's not able to do the Bianchi II transition. And that's where you see spikes, a very inhomogeneous structure. These spikes are first discovered by Berger and Vince Moncrief in the numerical study. Okay, and they call these spiky structures. And what they studied in the OTG2 spacetime turned out to be permanent spikes that form at the end of the Kasner era. But before you reach the end of that Kasner era, actually you can also have transient spikes. So these are spikes that form and then deform. And this happens a finite number of times because of the zigzagging. These spikes form and deform a finite number of times before finally forming as a permanent spike at the end of the Kasner era. In the more general G2 spacetime, if we drop the OT assumption, you have BKL dynamics, full BKL dynamics. That is to say, you have more than one Kasner era. So the permanent spike actually is a feature of the special OTG2 case. Okay,
what does OT mean?
Orthogonally transitive. It means the two Killing vector fields is action. The action is all special. Okay, it has a special condition on that. The permanent spite is actually an unfinished spite transition in the more general picture. My contribution to this research is the discovery of exact solutions describing the OT spite and the non-OT spites. And these are found by using the Randall-Weaver transformation applying on the Kasner seed solution. So that application will give you actually the Taub solution, and you apply it again on the Taub solution, and it gives you the spite solution. The non-OT case, I found this by applying Garrosh transformation on the Kasner solution. Okay, let me describe the spite dynamics. So again, we have the sigma plus, sigma minus state space. The spite orbits, well, as an inhomogeneous solution, here I've plotted different orbits along different world lines. So the red arrow here, the red line here, is the orbit of the spite observer. That is the world line at the spite, if you're exactly at the spite. And the blue one is along a world line very far away from the spite. And the purple ones are intermediate ones. Okay. Let's look at this case first. This is W is a parameter that describes a different member of the family of this solution. So for W bigger than 1, you have transient spite. Okay. So here at the spite, you go from here, this Kasner point, to that Kasner point. Whereas if you are very far away from the spite, you follow the usual spatially homogeneous BKL dynamics. So Bianchi II transition, the frame transition, and another Bianchi II transition. So the total change in the U index, you go from U to U minus 2, because here you have U minus 1, then U equal constant, and U minus 1 again. As you reduce W, this orbit morphs to, so W1 is the critical case. As W drops below 1, the final Kasner state they're different. So at the spite world line, you end up here. Whereas if you're at the non-spite orbit, you end up there. So you get this continuous limit. And that's the permanent spite. But it's actually an unfinished, more general spite transition. Before we get to that, so here I just want to show you a sequence of snapshots to see how the timing of these orbits. So going towards the singularity, you have this. So let me start again. So the faraway observers or world lines will undergo this Bianchi type 2 transition first. Then the spite world line would undergo its spite transition. At the same time, the faraway world line are rotating its eigenvectors of the n alpha beta. Then the faraway world lines complete its second Bianchi II transition. And everyone ends up at the same Kasner point. Okay, and this way, the solution, the spite forms and deforms again. So in this way, it is transient, but it's actually an oscillation, because what will happen next is there will be a frame transition that takes you down here, and the next spite transition happens. So it's a recurring thing. it doesn't go away. Okay. Now let's show the non-OT G2 SPI orbits. So this is what we see. This is what we would see in an OT-G2 case, the special case, where you get a permanent SPI, and this is it. It would just freeze like this. But in the more general case, you have an extra set of transition, which will take you away from this and continue and finish the SPI transition. So you end up at the same Kasner point again. Okay? So the main point I want to get across is that the SPI transitions are recurring, and it enriches the BKL dynamics. So previously, before discovery of SPIs, we see BKL dynamics as a sequence of Bianchi II transitions. And with the discovery of SPIs, we now understand that where these eigenvalues of n change of sign, and therefore you're unable to perform the usual Bianchi II transition, you get SPI transition instead. And SPI transitions allow you to actually still end up at the same Kasner point with all your neighbors after some time, after basically 2 consecutive Bianchi II transition for the neighbors. So this non-OT G2 SPI is a SPI transition that happens at the end of Kasner era. It happens between 2 Kasner eras, okay? Whereas the OT case happens within the same Kasner era. That's the difference between the two. So I'll end here by summarizing the kinds of states or spacetimes that we see as the spacetime reaches the quantum regime. So you take a cutoff time at the quantum, say Planck time. The most common state you would see in the BKL regime is a Kasner state. The next most common one are the Bianchi II or Taub transitions. For SPIs, these are rare because they happen at fixed surfaces. Actually, let's say x equals 0 surface or x equals 1 surface and so on. Whereas in between them, you get Taub transitions instead. The non-OT SPIs are even rarer because they only happen between Kasner era. So the open question is, how do we quantize these states? And that's what I'm here for. Thank you.
I think we can close this session, so thank you very much.
Thank you.